Greetings, students. Algebra 2, lesson 54. The topic is polar coordinates. Excuse me. New topic for us, new way of looking at graphing. I hear you saying, oh, graphing, I hate graphing. Well, you know what? This is a different kind of graphing. This is cute, fluffy, white, Arctic polar bear graphing, and it's going to be so fun. Just wait and see. Okay, a quick review. In the past, let's say that was a point that we were interested in. What we did was we located it on a graph by measuring a distance on the x-axis and then a distance, I'm making this up, on the y-axis. And we would say that the name of this point was 1, 2, 3, 4, the distance on the x-axis, and 1, 2, 3, positive and positive in this case. And so what we were doing was basically building a rectangle from the origin to the point and then measuring those distances. So this is what we would call a rectangular coordinate. With polar coordinates, our goal is the same. We've got a point on our grid, but we're going to use a different way to locate that point. We're not going to build a rectangle around it. We're going to do something different. We're going to use a location method that has two components. The blanks are where we're going to fill in the numbers. This cool sign is what we use to help write these numbers properly, and each point is described by a direction and a distance. The direction, I'm going to use our first example, is always measured in terms of degrees. And our distance is measured as a hypotenuse. You'll see what I mean in just a second. Hypotenuse. Okay, and in our first example, it's 4. So what we have to learn how to do is to take instructions like this and turn them into a location. That is our goal. So the first thing we always do is start with a picture. And in this picture, I happen to know that our point is going to be in the first quadrant. You know, remember how we have the quadrants numbered 1, 2, 3, 4? Well, this is positive, positive, right? And I just happen to know ahead of time that this is going to end up in the first quadrant. We'll talk about how I looking in the book, but you'll be able to figure that out yourself. So what we do is we always start measuring from what I think of as the horizon, the x-axis, and we measure backwards. So I start here and I measure 57 degrees backwards. Now, let's think for a minute about how far roughly that would be. All the way from here to here, that would be 90 degrees, right? Because this is a right angle, so this would be 90 degrees. If I went halfway, I don't want to write on there, but if I went halfway, that would be 45 degrees, right? So I want a little bit more than halfway, so I'm going to draw my angle about like that. And I'm going to scribble out the 45. I'm going to write 57 degrees. We're estimating that that's how big that angle is. I'm going to draw a line that connects our angle back down to the x-axis. We always draw our triangles so they connect back down to the x-axis when we're dealing with polar coordinates. And I'm just going to arbitrarily say that the length of this hypotenuse is 4 units. Whatever our units are. And so that means that's where I would find our point. Now this type of graphing is a little bit different than rectangular coordinates because we get to kind of say where the point is. There's no units here that require me to put it there. That's just where that point ended up in my picture. I estimated 57 degrees, and I drew a length of the hypotenuse, and I said, yeah, that's 4 units, because that's what I wanted it to be. Okay, cool. So that's how I draw my picture, but how do I find the name of this point in rectangular coordinates? Because that's my goal in this problem. Rectangular coordinates. But we're going to use a slightly different method for writing our rectangular coordinates. And I'll show you how that's going to work when we get to the end of this problem. Instead, I have to figure out the length of this side, which in the picture, which is really kind of kooky, John is calling this one P, and he's calling this side M. But in order to find the name of this point in rectangular coordinates, we have to figure out this measurement, right? Because that's what our first number will be. So we have to find the length of P, and then we have to find this measurement, that's equal to the top here, because that will be the second number in our rectangular coordinate, and that is the length of M. So if I can find the length of P and the length of M, that will be equal to my X and Y, like so. So how are we going to find the lengths of these measurements? Well, we have the tools. I want to find X first because that will be the first number in my pair. Well, this is the adjacent side, isn't it? And I've got the hypotenuse, and I've got the degree measurement. So we can use our trig tools to find the length of P. It will be cosine, right? Because cosine is the adjacent. So the cosine of 57 degrees will equal P over 4. Because, let's just jot this down. Sine, cosine, tangent, Oscar had a hold over Arthur. So to find the adjacent over the hypotenuse, I use cosine of 57 degrees. And so I can also fix cross multiplying to say that P will equal 4 times the cosine of 57 degrees. I just cross multiplied those and then had them flip sides with P. Similarly, I'm going to put a little squiggle here. The sine of 57 degrees, sine is opposite over hypotenuse, that will give me M over 4. And so again, I can cross multiply and rewrite this to say M equals 4 times the sine of 57 degrees. We're going to use this process over and over and over again when we're converting polar coordinates to rectangular, because these measurements, these sides of the triangle, the adjacent and the opposite, are the same number as the X and the Y in our rectangular system. Okay, so, excuse me, flipping merrily, we grab our calculators. I can't grab mine, it's busy recording this for you. But I can tell when we do the work of that, M will be equal to 3.36. Give or take, you know how John is with rounding, and P will be equal to 2.16. So what that tells us, let me go back here. So P, I said, was equal to 2.16, and M was equal to 3.36. Those are the lengths of those sides. Those are also the numbers we need to write this in our rectangular coordinate system. We could write them as, I'm going to go over here and work in this space. If we use this formatting style that we used before, we would write 2.16, comma, 3.36. That would be a perfectly accurate way to name this point using rectangular coordinates. That's fine. The problem is that if we use a slightly different style, we're going to be able to use these numbers in really cool ways in the future. We're not quite there yet. But we want to use a slightly different formatting style so that we can do some new tricks further down the road. So what we want to do is we want to orient ourselves at the origin and think on the x-axis, we're moving, to get to the place we want to go, we're moving 2.16 units in the positive direction, I guess you could say in the direction of the right, right? We're moving to the right-hand side in a positive way. So we write plus 2.16 R, standing for right. If we were moving this way, if our point was over here, we would say negative 2.16 R. We'll get to that in a later. Just right now we're doing positive, so that's easier. To measure this direction, the 3.36 that we had here as our y value, if you will, instead of measuring that on an axis that we're calling the right axis, we're going to call this one the up axis. So going up from the origin in the positive direction is plus 3.36 u, standing for up. If our point was down here somewhere, we would say negative whatever the number up. So positive right, negative right, positive up, negative up. Clear as mud, right? It's a little confusing now. It's going to make more sense later. And this is fabulous because when we format our rectangular coordinate this way, we're going to be able to do cool things with it in the future, like I said. So this is our final answer for this problem. That is the name of this point. It's the very same point as this notation describes. It's kind of like two treasure maps to the same place. And one uses one kind of clues and the other uses the other kind of clues. And what's cool is that we're so smart is that we can use one set of clues, find the point, then write the treasure map instructions in the other set of notations. So that's really cool. I know you're impressed. Okay, that was the end of that one. Let's try another whack at these. We've got 3 total problems of polar coordinates that we're going to take a shot at here. This time we're asked to change this polar coordinate 7 at 230 degrees. Okay, that's the way we say that. 7 at 230 degrees. Remember, this is the direction. It's the angle measurement that tells us what direction we should head in. And this is the distance, which is the hypotenuse of the little triangle we're making. So, we start, last time I just told you the first coordinate. This time we have to figure it out. So this time I'm going to draw the whole 4 quadrants. We always start here, and we go counterclockwise as we measure our angles. Now, we have to go 230 degrees from this starting point. Whoa. Well, we know this much. I'm going to dot it. That much is 90 degrees. If we go another quadrant, it's 180 degrees. We have 230, so what I'm going to do is subtract so I can find out how many more degrees I have to travel. 50 more degrees. Okay, this is 90 if I go the whole way, so I want to go a little more than half, don't I? Just pretending that that is 50 degrees. Just guessing, taking a shot at it. I always draw my line back to the x-axis, or the right axis, as we're calling it now. Now I've got a triangle, and I know I'm going to be using my trig values on it, so I need to figure out what that angle is. Well, we figured it out right here, right? There's 180, or 90, 180, and then plus 50 more. So this is a 50-degree angle. It doesn't matter that it's hanging down here in the 3rd quadrant. That's fine. But this, our whole treasure map instruction said to go 230 degrees. But this triangle that I've drawn, that I'm going to perform my trig tricks on, this angle is a 50-degree angle. Cool. Now what about our distance from the origin to this point that we've arbitrarily drawn, or I guess I drew it. We're calling that 7 units. That's the hypotenuse of the triangle that we made. So to convert this into rectangular coordinates, we know that we need this value which, if we're standing at our angle, oh yeah, that's the adjacent, isn't it? And then we're gonna need, let me draw this a little more. We're gonna need this distance, which is the same as this side, which is the opposite, and that's our sine value. So, I'm gonna say 7 times the cosine of 50 degrees will give me, what should we call this? Let's call this A for adjacent. Equals, no, that was right. The way I had it was right, because I already multiplied by my hypotenuse. Remember back here, where we wrote it out the long way, and then we cross-multiplied and simplified? We can do that now. We know that the side we're interested in is going to be equal to the hypotenuse times either sine or cosine, whichever one we're looking for, and then the degree measurement of our triangle. So I can do a shortcut. The adjacent side will be equal to the hypotenuse times the cosine of our triangle. Notice that it's not the degree measurement here, it's the angle that we created in our acute angle triangle here. And then this will be the opposite side. The opposite will be equal to the hypotenuse, this time times the sine of 50 degrees. And when we do the math on the calculator, again, I'm relying on John because my calculator's busy. The sine value is 5.39, and the cosine value is 4.48. Let's look and see if that makes sense. So, cosine is adjacent 4.48, and this is, we're saying, is equal to 5.39. Right? Cosine is adjacent, so that's the value of the adjacent side, because here's our angle. And then sine is opposite, so this is the opposite side, 5.39. Given that our hypotenuse is 7, that looks fairly logical. Okay, so now that we have those sides calculated using our trig functions, the only thing we have left to do is write this in the proper notation. So first we look at the distance on the right, or x-axis, and we see it's 4.48, but it's in the negative direction from the origin. So we write this as negative 4.48 to the right. And notice this is our up axis now. We're in the negative ups. Does that make sense? Because we go down from the origin. So we say negative 5.39 up. And that's our final answer. So again, this is one name for this point, and this is another name for this point. Polar coordinate, rectangular coordinate. They both lead us to the same place, and we can translate. Right now we're just going from polars to rectangulars. Later we'll learn how to start here and go there. Okay, now that I've confused you thoroughly, let's do one more example. And this is example 54.3, and this time we're doing 42 at 340 degrees. Okay, these numbers are bigger, but they do not scare us. So here's what we do. Again, let's just, until we get really, really fast at snapping into our degree measurements, let's just go ahead and draw all four. Later you'll be able to do some of this in your head, and you can just focus in on the quadrant you want. Okay, 340 degrees is how far we have to travel from here, counterclockwise. We know that if we go the whole circle, that will be 360 degrees. So 340 degrees is going to be just, I'm going to write it on the outside, 20 degrees short of our distance, right? 340 takes us like this. So the angle that we're talking about, and we always draw our triangle back to the x-axis, or the right axis as we're calling it now. We never draw it, we never would go from here back to here. We always draw it back to this axis. That's how we make our triangles. Here's our right angle. So this is 20 degrees because it's the little sliver that's left after we take our 340 degrees, and our hypotenuse, because this is the hypotenuse, is 42. Now notice that I don't have to make little hash marks and show that that's 42. I just get to say, that length is 42 degrees. It's as easy as that. So in some ways, polar coordinates are way easier than rectangulars because we don't have to make all those silly little markings. Okay, beautiful. So let's figure out what we need to know in order to write this as rectangular coordinates. First, we need this distance, because this is going to be our right distance, and that's the adjacent side. I'm going to call it A again. And then we need this side, because this is like the X, or the Y value rather, right? Because it's the distance on this Y-axis, or as we're calling it now, the up axis. We'll call this opposite. So 42 is our hypotenuse times the cosine of 20 degrees will give us this value. Cosine gives us adjacent, that's what we want. To find this distance, we'll do 42 times the sine of 20 degrees, and that will give us our opposite side, which again, we could measure it here. It's going to be the same distance, that's what we want to get to that point. Okay, so we measure it out here on the triangle, but remember it's the same thing that we would measure there. Okay, relying on John to do the math for me, I get that A is equal to 39.48 units, whatever the heck they are, and the short side, O, is equal to 14.28. So let's see if that makes sense. We're saying that this side is 39 and some. That makes sense because it's almost as long as 42, and then this guy should be considerably shorter, and he is. He's 14.28. Okay, so we've got our lengths. The last thing we need to do is to write it in the proper format. So we start by looking at our right measurement. Okay, it's a positive right. So we write plus 39.48 to the right. But now our up measurement is in the negative. So then it becomes negative 14.28 to the up. It's a negative up, right? That makes sense. But it kind of does. When you look at the answer, John leaves the plus sign off here. That's okay, but I like to see that plus sign so that it's crystal clear what you mean, up or down. Okay, 3 examples of taking this weird new polar coordinates that have a direction and a distance and converting them to a weird version of rectangular. Remember, these are rectangular coordinates. They're just in a different, slightly different format, and like I said, that's going to come in super helpful a few lessons from now. This is our polar friend. Both of these notations represent the same point. It's just 2 different ways of saying them. Okay, enough about that. Topic B is super short and easy. It involves similar triangles, and it's super straightforward and kind of fun. Let's draw a little bow tie pasta here. We have said that similar triangles happen when our triangles have matching angles but different sides. And here we are told that these 2 angles are the same, and we know that these 2 angles are the same because they're vertical angles. So if we have 2 angles the same, then we know we have 3 angles the same. Clearly these sides are not the same length, but we can use them to solve proportions. And here are C, B, and D. Now, we can say that, I'll use the way, John sets it up in a way that I think looks a little weird. He says the length of side C in proportion to side A is equal to B over D. And I agree, these two sides are the same, well, they're proportional, and these two sides are the same. Okay, so I would have done A over C equals D over B, but whatever, it doesn't. Now, we have this proportion. We don't have any numbers, we just have letters. So the point that John says, the point that John makes is that we can solve this for any letter that we want. We would start by cross multiplying, right? We'd say CD equals AB, I'll put them alphabetical, and now we could solve this for any one of those four letters because it's an abstract equation. So we look to John and he says, if we want to solve it for D, well, what would we do? We would divide equals, why is this not right? No. C over A didn't I? According to John, this should be C over A equals D over B. And then when we cross multiply, we would have CB equals AD. And then when we solve for D, let me cross that out, we would have D equals CB over A. This is the correct answer. So I messed up here when I was setting up the proportions. So this is the right way. Thank you, John, for saving me. Okay, so all we're really doing here is instead of using any numbers, we are using all letters, and then we're just solving in the abstract, which is easy. There isn't even a problem to do with this. So that, my friends, is lesson 54. I hope you enjoyed it as much as I did.